For more than 100 years, a strange puzzle has sat out in the open, baked by the Egyptian sun. In the granite quarries near Aswan, deep curved scoop marks are gouged into bedrock that's harder than steel, and no explanation has ever fully accounted for them. They used pounding stones, some historians claimed, copper chisels, said others, but when a research team recently ran high-resolution images of these strange marks through an AI system and asked it to work out what actually happened there thousands of years ago, the results reshaped how we think about ancient engineering, and the answer wasn't the one most people expected. This is the story of how that AI analysis helped crack a puzzle that had stumped archaeologists for generations. The story starts at Aswan, a site that has drawn archaeologists for generations. It was here that ancient Egyptians pulled some of the hardest stone on the planet out of the ground to build monuments meant to outlast entire civilizations. The unfinished obelisk still sits exactly where its builders left it. Roughly 5,000 years ago, abandoned mid-cut, frozen like a snapshot of ancient work in progress. Had it been completed, it would have stood about 42 meters tall and weighed close to 1,168 tons, making it bigger than any other known Egyptian obelisk. So how did they manage it? That question nagged at researchers for so long that some turned to far stranger explanations, lost technologies even outside intervention. Those ideas caught on partly because the ordinary explanations never seemed to measure up to the scale of the achievement. For decades, the accepted academic answer was simple. Mark Lenner, a well-known Egyptologist at Harvard, argued that workers relied on dolerite pounders, hard, dense, dark, igneous rocks shaped into balls ranging from fist-sized to head-sized to slowly beat the granite down. The evidence seemed to back this up. Archaeologists had recovered large numbers of these dolerite hammerstones scattered around the Aswan quarries. PBS's Nova even filmed a reconstruction, proving the method worked, if painfully slowly. For over a century, that was good enough. The reasoning felt sound, plenty of workers, plenty of time, plenty of patience. Not elegant, but plausible. Still something never quite fit. Pounding stone with dolerite hammers produces jagged, unpredictable fracture patterns. But the curved scoop marks at Aswan were oddly uniform, almost mechanical, as if made by a repeated, deliberate motion rather than random battering. That mismatch bothered researchers for 100 years. But without a better theory, the pounding story stuck around by default. In early 2025, a team of digital archaeologists at Heidelberg University decided to look at the evidence differently. Instead of leaning on tradition, they turned to modern imaging technology, gathering high-resolution photos and 3D scans of tool marks across the quarry, documenting cut angles, trench depths, and surface textures on the unfinished obelisk in detail. Then they fed all of that raw data into an AI model and asked it a simple but pointed question based purely on the physical evidence. No prior theory, no scholarly assumptions, what methods were actually used to cut this stone. The answer wasn't a simple confirmation of what everyone already believed. It showed that the traditional story, while not wrong, was incomplete and in places misleading. The marks didn't point to a single technique. They pointed to several methods layered together, each suited to a different stage of the work. Alongside the dolerite hammerstones, excavators had also found large amounts of charcoal ash and burned mud bricks scattered through specific parts of the quarry. Not random debris, but the leftovers of a deliberate process. That evidence points to fire setting as a key part of the quarrying process, especially for breaking large blocks free from the bedrock. Fire setting is an old technique used by multiple ancient cultures. Workers build fires against an exposed rock face until it's heated through, then douse it with water. The sudden temperature swing creates internal stress that cracks the stone along its natural weak points, much faster than pounding alone. Ancient writers described exactly this. Diodorus Siculus, writing around 60 BC, described fire setting in Egyptian mines and quarries. Pliny the Elder gave an even more detailed technical account in his Natural History. These weren't guesses. They were descriptions from people who'd seen the process or spoken with those who had. The quarry itself backs this up. Ash and charcoal traces turn up, not just at the unfinished obelisk, but elsewhere in the granite fields too. Nearby vertical shafts, each just under a meter wide and several meters deep, may have served as control points, helping workers set the depth, width, and alignment of the obelisk before fire setting cleared away the bulk of the stone zoom in further, and the picture gets more layered. Still, tool marks on finished granite boxes from the 4th dynasty suggest a rough shaping stage with pounding stones, followed by fine finishing with abrasives. Copper and bronze were available, but both are too soft to cut granite directly. The real workhorse was sand, specifically quartz, sand abundant across Egypt, and dragged back and forth with a copper saw, it slowly ground through even the hardest stone. In 1999, researcher D. A. Stocks tested this directly at Aswan, using a copper blade modeled on ancient dimensions. One 8 meters long, 15 centimeters deep, just 6 millimeters thick. He tried it wet and dry, smooth-edged and notched tracking results carefully. In one run, workers cut a 3 centimeter deep, 95 centimeter long slot, roughly the height of a person in 14 hours of steady sawing. Slow by any modern measure, but the ancient Egyptians weren't short on time or labor. Dry sand with a smooth blade cut fastest. The copper blade itself wore down by about 7 to 5 millimeters over the course of the work proof that the sand was grinding, tool and stone together with the copper, acting mainly as a carrier for the abrasive. The same principle applied to copper drills used with sand and water to bore into granite. Some researchers think harder abrasives like emery, a form of corundum, might have supplemented the quartz sand for tougher jobs. Flint chisels struck with dolerite hammers likely handled detail work too. One 15-inch flint chisel turned up in Khufu's boat pit. What emerges is a multi-stage process refined over generations, rather than improvised on the spot. Scouting weak points, workers identified natural fracture lines in the granite. Scoring flint chisels struck with dolerite hammers cut initial guidelines along those weaknesses. Fire-setting controlled heating and rapid cooling snapped large sections free along the pre-cut lines with far less waste than pounding alone, shaping coarse quartzite. Abrasives brought blocks closer to their final form. Finishing progressively finer quartzite and copper saws or drills paired with wet sand produced the smooth, precise surfaces still visible today. That sequence lines up with what's actually stamped into the stone, rough, irregular marks near the surface, giving way to smoother, more uniform ones deeper in, including those long, mysterious, curved scoop marks now explainable as the signature of repeated sand and water grinding. The AI analysis didn't invent new evidence. What it did was tie together threads that had mostly been treated separately. Hammer marks, ash deposits, historical texts, and modern replication experiments into a single internally consistent account of how the work was actually done, stage by stage. The Doleritenly story went wrong exactly. It just described one part of a bigger system. Pounding handled the rough early work, fire setting handled the dramatic bulk removal, sand, water, and copper tools handled the fine, precise finishing. None of it required lost technology or outside help. It required a deep, practical understanding of how granite behaves, where it's weak, how it responds to heat, how abrasives wear it down, paired with enormous patience and organized labor. That's also the real point behind the impossibly precise granite boxes and sarcophagi that fuel alternative history speculation. Once you know the actual sequence of tools and techniques and see modern experiments reproduce similar results, by hand, the precision stops looking mysterious. It looks like the product of skilled people who spent their careers mastering one material. Ancient texts back this up too. They praise workers' strength and dedication and describe the scale of labor involved, but never gesture at some hidden or unknown technology. The picture that emerges is one of well-organized, experienced labor, applying a system refined over centuries, not a shortcut or a secret. This case also says something about how useful AI can be as a research tool in archaeology. Human researchers can get anchored to long-standing interpretations, a model built to work directly from the physical evidence, the scans, the residues. The marks isn't carrying that same baggage and can sometimes spot a coherent pattern across data that had previously been treated in separate silos. If that doesn't replace archaeologists, someone still has to interpret the evidence responsibly and know where the data stops supporting a conclusion. But it suggests similar approaches could help with other long-standing puzzles in ancient engineering, from pyramid construction to other unresolved quarrying questions. The unfinished obelisk remains the best classroom for all of this, because it was abandoned. Mid-work its surface preserves the entire process, layer by layer, largely undisturbed by later weathering or reuse. Read carefully with laser scanning microscopy, and now AI-assisted pattern recognition. It tells a clear, consistent story. The Egyptians didn't need advanced machinery or unexplained technology to shape granite on this scale. They needed a working knowledge of their materials, a willingness to combine several techniques, and the patience to apply that knowledge across generations. The evidence was there in the stone the entire time. It just took the right combination of tools, old and new, to read it clearly.